Hello and welcome back to 5.1 Models of the Atom. We had been talking about this idea of atomic orbitals. These orbitals indicate where an electron is likely to be found about 90% of the time. So kind of like a surface within which an electron is going to be located with the highest probability. Electrons exist in these atomic orbitals, which are also known as density clouds. These orbitals have different shapes and they can be kind of unique. They're referred to as S, P, D, and F orbitals. We're going to talk more extensively about these different shapes and their designations today. Now, Bohr was on to something when he said that the one electron in a hydrogen atom could only exist at particular distances from the nucleus. What he had discovered was the principal energy levels that could be possessed by the electron. In the quantum mechanical model, these energy levels are labeled by the principal quantum number, written as a letter n, which must be a whole number value. And as you can see in the diagram to the right, it designates energy levels, meaning how far out from the nucleus these things can exist. So the principal quantum number refers to which energy level, with the low numbers of like 1 and 2 being close to the nucleus, and higher numbers, those would be orbitals that are much farther away from the nucleus in their outer boundaries. Now, each of these energy levels may contain different sublevels, and those sublevels vary in shape, and they also vary in the amount of energy that they possess. Now, each principal energy level is limited in the number of sublevels it can possess. At the first energy level, with a principal quantum number of 1, it can only have one sublevel, and it's called the S sublevel. When we have the principal quantum number of 2, it can have 2 sublevels, and so there's an S sublevel as well as a P sublevel. With a quantum number of 3, it can have 3 sublevels, S, P, and D sublevels. And the fourth energy level can have 4, S, P, D, and F. We also have principal quantum numbers of 5, 6, and 7, so theoretically they could have that many sublevels to them. So like n equals 5 could have up to 5 sublevels, S, P, D, F, and something else, G or something like that. But in reality, we end up running out of electrons before we ever have an electron go into a 5G sublevel. Perhaps as we create heavier and heavier elements, we may create someday one that has enough electrons that it requires a 5G sublevel. Now, I mentioned that the S sublevel exists at the first energy level. It also exists at the second energy level, and so forth. You notice they all contained an S sublevel. The question is, how does a 1s sublevel differ from a 2s sublevel? Or, if we're looking at it in terms of orbitals, how does a 1s orbital differ from a 2s orbital? And as you can see in this upper right-hand picture, it's really all about size. A 1s orbital is much smaller than a 2s or even a 3s. So that corresponds to the amount of energy. The electrons that can exist in the 2s orbital possess more energy than electrons that can exist in a 1s orbital. That's why they can move further away. And in a 3s, they possess more energy yet. Now, what about p orbitals? How does a 2p differ from a 3p orbital? In each of these orbitals, you should notice that they have 2 lobes. So they might kind of look like a dumbbell. Frequently, we refer to these as being dumbbell-shaped. But notice the 2p and the 3p, they look pretty much the same. They're just different in size once again. So the 3p orbital extends out further because those electrons possess more energy, so those orbitals are bigger because the electrons have enough energy to move further out from the nucleus. Notice they're also pointed in different directions in space. In three-dimensional space, we have x, y, and z axes, so they can point in those 3 different directions. So, as you can see in this picture, even when we're at the 2p sublevel, there are 3 different orbitals known as 2p orbitals. and we need a way to differentiate between them as we talk about them. So we talk about them in terms of the three-dimensional axis on which they're aligned. So we might call one a 2px because it's lined up along the x-axis, another one the 2py, it's aligned along the y-axis, and of course the 2pz is lined up along the z-axis. So each sublevel, S, P, D, or F of a principal energy level, 1, 2, 3 through 7, etc., has its own number of equal energy orbitals that it can contain. The S sublevel always consists of just a single spherical orbital. If you think about it, it's impossible to have spheres of the same size centered around the same nucleus and call them different spheres, because they're occupying the exact same space, three-dimensionally speaking. So there's only a single 1s sublevel, and there's only a single orbital within that 1s sublevel. The 2s sublevel contains just a single s orbital at the 2s level, which is just a bit bigger than it is at the 1s level. The p sublevel always consists of 3 dumbbell-shaped orbitals. These are oriented, as I mentioned previously, along the 3 different dimensional axes and are equal in energy to each other. So we have a px, a py, and a pz, whether we're at the second energy level, the third, the fourth. If it has a p sublevel, then there are 3 equal energy orbitals that are found there. Now the d sublevel has more complex shape to it. Notice there are 4 lobes for most of these diagrams, and so we frequently call it a double dumbbell shape. 4 of these 5 d orbitals have the same basic shape. The first 2 and the last 2, and that one in the middle looks kind of weird. These are all turned different directions in three-dimensional space, which is why we say they're different orbitals. When you put the first 2 and the last 2 together, they take up all the space around the nucleus of an atom, except for a little bit above it and a little below it, and kind of a ring around the middle, which is why you've got that 5th strange orbital that you find in the middle of this diagram. And to keep it simple, although they have a lot more complex names than these, we're going to just call them D1 through D5, just to keep it easy. And finally, if we look at the F sublevel, an F sublevel always consists of 7 orbitals. These are pictured on the right and are very complex, as you can see. Many times they say F stands for flower shaped, right? Because there's lots of lobes to it, kind of like petals on a flower. They're also turned along 7 different orientations around the nucleus. To simplify them, we'll just number them 1 to 7. Don't worry, you're not going to have to be able to distinguish F1 from F6 or anything like that, but you should be aware that they have lots of lobes like this, that there are 7 of them, and yeah, there is one that's got a really strange shape to it, a lot like that single one that looked different for the d orbitals, only this one has 2 lobes and 2 rings around the center. Now, we talked about a lot of different orbitals there, and each orbital can hold up to 2 electrons. It doesn't matter if it's a 1s orbital or a 4f7 orbital, it can hold up to 2 electrons. In this diagram, we can see a 1s orbital kind of shown in blue in the center. It's sphere-shaped. We see a spherical 2s orbital that's bigger than that one. And then we see these red lobes going around that are the dumbbell-shaped 2p orbitals. And there are 3 of them pointing along the x, y, and z axes. And finally, we see a 3s orbital pictured here in white, which is bigger than the 1s or the 2s were. Now, when you describe the location of an electron in an atom, it's a lot like giving an address. Only it's given, in this case, from the least specific information to the most specific. We start with the most general, the principal quantum number, and we go down towards the most specific. So you've got to understand that the general information is what energy level is it at. That's the principal quantum number. Within each of those, there's a sublevel. Sometimes 1, just an S at the 1s. Sometimes several, like a 4th energy level would have a 4s, 4p, 4d, and 4f sublevel. So it has 4 sublevels at the 4th energy level. Then there's a more specific designation. Many of these sublevels have multiple orbitals. So when I say it's at the 2p sublevel, I need to say which orbital it's in. Is it in a px, a py, or a pz? Or maybe we're dealing with a d sublevel, so there's 5 different d orbitals that I might be discussing, like 3d1, 3d2, 3d3, 3d4, or 3d5. And of course there are 7 at an F sublevel. I'm not going to run through all of those for you. And finally, something we've not discussed yet. I mentioned just a little bit ago that electrons can fit into an orbital 2 at a time. And you may say, how is that possible? Because electrons are negatively charged, and so they're not going to want to stay near each other in an orbital 2 at a time. But they're electrons. They're negative. They're going to repel. But these electrons, we can think of them as spinning objects. And as they spin, they create a magnetic field. And if one's spinning one direction and the other one's spinning the other direction, their magnetic fields complement each other, and you end up with North Pole next to South Pole and South Pole next to North Pole. And it overcomes that repulsion of the negative charges because of the magnetic field that's created that holds them together. So our final, most specific pieces of information about electrons is their spin quantum number. And really it's not a number at all. Your book uses either an up arrow or a down arrow to indicate they're spinning in different directions. So to review, our most general piece of information is the principal quantum number. It represents the main energy level or shell. It's only a positive integer such as 1, 2, 3, 4, 5, etc. Smaller numbers tell you that that electron is located closer to the nucleus. As n, the principal quantum number, increases, energy of that level increases as well. And our known elements use principal quantum levels from 1 through 7 only. The number of electrons in a particular shell or energy level can be found using the expression 2 times n to the second, where n is the principal quantum number. So for, let's say, the third energy level, we'd square the 3, get 9, and take it times 2, and it can contain 18 electrons total at the third energy level. So if I asked you the questions, how many electrons can fit into the first energy level, you could just use this equation and say, I put the quantum number of 1 for the first energy level into this equation. 1 squared is 1 times 2 is 2. So this answers it without us having to understand how many orbitals there are, how many electrons fit in each, and adding it all up in our head. And we've already done the third energy level. The sublevel designation is shown with the principal quantum number followed by the sublevel. So examples of sublevel designations are things like 1s, 2s, 2p, 3s, 3p, 3d, and it would go on, 4s, 4p, 4d, 4f, etc. The sublevel designation indicates the shape and energy of the orbitals contained by that sublevel. And we can see them depicted at least for S, P, and D sublevels in this diagram. The number of possible orbitals is equal to the principal quantum number. Keep that in mind. So if we're at the fourth energy level, that's the fourth principal quantum number, then there are 4 orbital shapes possible. First of all, to discuss the orbital designation, we need to first understand what an orbital is. An orbital is a region within an energy level where there is a strong probability of finding an electron, usually shown with 90% probability. Remember, only 2 electrons can occupy one orbital. Orbital designation describes the orientation of an orbital around the nucleus, three-dimensionally speaking. In other words, in terms of x, y, and z axes. For an s orbital, there's one orientation, so there's just a single orbital there. P orbitals, there's 3 different orientations, so a p sublevel has 3 different orbitals. The d sublevel has 5 different orientations, so there's always 5 d orbitals. And f orbitals, there's 7 of those at an f sublevel. And so it's easy to remember these. If you notice, you're counting by odd numbers. S, P, D, and F are 1, 3, 5, and 7. Here we see depicted an s orbital. It has a spherical shape that's centered around the origin of the 3 axes in space, and right at the origin would be where the nucleus is located. P orbitals are dumbbell shaped. There are 3 p orbitals beginning at the second energy level. All p sublevels, whether it's the second energy level or the 5th energy level or whatever, have 3 orbitals, and we call them px, py, and pz, depending upon their direction of orientation. There are 5 different d orbitals, and they begin at the 3rd energy level, because remember, the first only has an s sublevel and the second has an s and a p sublevel. So the 3rd has s, p, and d sublevels So it's at the third energy level that we finally see d orbitals. And finally f orbitals, which are stranger yet, but they have flower shapes for most of them. Finally, electron spin describes the behavior of an electron within the orbital, meaning the direction of its spin. To be in the same orbital, they have to have opposite spins. Your book designates these spins using arrows up or down.